Nice. Hello, everybody, and thank you very much for the opportunity to present my research for such polymer community. Yeah, my topic is hydrogel colloidal particles functionalized with the silver nanoparticles as drug delivery and sensor systems. And really, I'm thinking how to start my talk because depends on the community usually start or how the hydrogel is nice or how the particles is nice. But okay, I start with the materials now. Yeah, because really hydrogel has a lot of applications, and in our lab we partly touch few of them, like we try to use hydrogel for the food encapsulation, and here this example of the encapsulation of the kind of molecular kitchen, like the nice caviar with liquor inside. Also for wound healing tapes, contact lenses, and bone tissue engineering, and as well as the drug delivery. Really, most of you, I think, here's a few of these applications or touch, like the contact lenses and wound healing is also quite common. But for drug delivery, the hydrogels not so common yet, and especially the alginate-based hydrogels. And really, in my talk, I will try to explain why and what possible to do. I mean, with it, what are our progress in this area. Really, create the capsules from the hydrogel. It's very easy and it's very cheap because you can take the sodium alginate powder, which are quite cheap and available in a normal store already, and kind of calcium lactate, and you can just drop them to the cross-linker solution and get kind of sterilization. And this one you can easily find a lot of movies in YouTube how to do any caviars from any possible eatable compounds. Yeah, but the problem of this method that such capsules is quite big. Usually it is 2, 3, 5 millimeters. And of course, if you go from your kitchen to the lab, you can take the needle, you can take the kind of pipette and can decrease the size, but it still will be millimeter or half millimeter, which kind of too big for real drug delivery application, especially for intravenous administration. Of course, for deliver something in stomach, it's okay. But if you would like to increase the ability of such capsules, difficult. But for delivering stomach, it's already exists kind of gelatin capsules, and its market is too tough already, I think. Yeah. And in our work, we try to think how to decrease the size of such hydrogel compounds. And one of the ideas which come from, we think to use the templates methods. In the case, we can think, okay, we can absorb the alginate layers on the kind of hard template and create or layer by layer or cross-link on top. This one already quite well-known methods for this, and maybe we can get a nice capsules. And really, first of all, what type of template we should choose? Really, there are a lot of templates available in layer by layer technology in polytoid capsules, in hydrogel capsules, and usually it is a kind of common polystyrene, porous silica, melamine formaldehyde, but all of them sometimes necessary very kind of aggressive substance to dissolve them, like the tetrahydrofuran and so on. And really, this one provides us a lot of limitations what type molecules we can encapsulate, because they should be resistible. In our case, we're thinking that it will be nice to use something more friendly for environment and which are much more easy to dissolve, like the calcium carbonate, for example. In our lab, yeah, we developed calcium carbonate particles before for a lot of different purposes by themselves. And here this I should remind that calcium carbonate is like the diamond, like the carbon, exists in few modification, like depends on the crystallographical structure. Like the aragonite is the needles, look like particles which exist in the kind of seafood shells. Calcite, which if you teach in blackboard, you always touch as a part of the chalk, and it's look like in the same images as a cubic. And also the vaterite. And vaterite here, I don't have any kind of nature minerals, because usually it's fluored water, which I discovered them in alpine area kind of 100 years ago. The problem is that it's quite unstable minerals which exist, which easily recrystallize to the more stable form, like calcite or orgonite, depends on the water present or another kind of conditions. In the case, it's very difficult to find them in nature, but it's not so difficult to synthesize them in a lab. For synthesizing them in the lab, usually it is, it's very cheap technique, and you need to know just conditions, how to do it. If you take the kind of source of the calcium, for example, calcium chloride, and source of the Cu2 ions, for example, or sodium Cu3, or just sparkling water, mix them and stop this reaction kind of time, you can get the kind of nice porous water-like particles. Why we are interested in it? Because calcium carbonate is easily dissolved in any acid. It's easy to dissolve in calcium complex, in solution which create complex with calcium, like the EDTA. And as well, it's very cheap and porous. And they can absorb any ions and molecules on top. Okay, really, if we start change different conditions, for example, molarity, start adds a kind of other solvent to the mixture to slow down the reaction, we can reach different sizes, shapes of the particles, which could be template for our following polymer capsules. Yeah, for example, here's the example how we change the molarity ratio, give us different kind of crystals, like from spherical to star-like or cauliflower-like, which after this we can use as template. And really the problem is this reaction is quite unstable, and every change in the time and temperature leads to the crystallization, because it's mass crystallization effect, and it's a lot of reactions happen at the same time. In a time we standardize this reaction in the reactor and start study how we get them in grams, such porous particles. And really here, we find few solutions, but we still don't have a kind of global figure how to synthesize such nice particles, because from lab to lab, from magnetic stir to magnetic stir, sometimes it changes because the temperature and salt concentration and viscosity, sometimes it's a bit different also in the same lab. And we start use here the machine learning approach to synthesize, to help us to predict the result of the synthesis. And because also we don't need just these particles, we need also the kind of property of them, how they better absorb the polymers and how they use them for after this for drug delivery system. And really we use a lot of, we go to the kind of machine learning and start to do the predictions of our synthesis, and was quite successful to predict, for example, as example, the property, because we need the water right here, and to predict the crystallographical property of our particles and determine what the factors more important for them. For example, here it's one of the examples of our work that we check what is more important: temperature, viscosity, salt concentration, or time for particle synthesis. And we use two approaches, like the kind of white box and black box, and both of them show to us that the temperature is more important and allow us to predict what phase we have in exactly these conditions before we doing synthesis. Of course, there is kind of very high probability, it's around 95% we predict correctly, but in exact temperature and time frame. Yeah, but of course, after use a lot of different synthesis and check a lot of conditions, what we get as result. We know the conditions how to synthesize the spherical particles from 300 nanometers till 12 microns. And also we know how to do the elliptical particles with axis ratio around 2. And also the star-like particles up to the 3 microns. But really for the next step, to apply such particles and as template for kind of drug delivery, we start thinking, okay, we don't like to have just drug delivery and deliver them. We like to realize maybe theranostic concept that we have just drug carrier and sensor and one object. And start thinking how to activate the drug, dependent on the kind of diagnostic results, maybe which could our particles provide. Yeah, first of all, to create drug delivery system, we need to know how to load the particles. Since we have the core, our calcium carbonate is a core, we can load any kind of drug, which are water soluble or kind of in normal pH, to the particles just via absorption or via the co-precipitation during the synthesis, because all our synthesis in water. In the case, it's very easy to upload any enzymes or any water-soluble compounds. Really, just we have here two limitations when we load. One of them, it is it's difficult to load ions because it's just small amount and it's very difficult to detect them. Second one, if it is in low pH compound, because these particles start to be dissolved, because calcium carbonate very sensitive to the pH. Here it is in this slide we have the example, for example, of loading the particles with a rhodamine 6G, and quite the same with the doxorubicin by the property in our case, and we see that the drug penetrates really inside the particles, and when we do the two-photon microscopy, it's everywhere, it's inside and outside, it's a few whole pores of them completely. Porosity of the particles, it's around 50% inside. It's not a lot, but kind of. And the surface of the particles around 20 square meters per gram in the best way, but of course it depends on size, shapes, and so on. Yeah. Okay. Now we know how to load something on template, and we can try to use such calcium carbonate to create polymer capsules, polymer shells. For this one, we start using such approach. We adsorb the molecules like the alginate, and after this, we start cross-link them with the silver. When we cross-link the alginate with the silver, they create kind of form a shell around and start to be repeat our porous structure. And after this, of course, we can do it with the calcium as well, and we do it, but with silver just here, it's more interesting because if we cross-link them with the silver, and after this at ascorbic acid, we do two reactions in the same step. The calcium carbonate start to be dissolved because it is acid, and the calcium ions start to be released and start to be hollow. From other hand, in the same time, the silver start to be reduced because it is acid, which stimulates the reduction of the silver, and silver nanoparticles start to be grown from the ions. And as a result, we see it's not will be just kind of silver alginate gel particles like the gel. It start to be shell of the silver nanoparticles connect with the hydrogel molecules without any templates inside. Yeah, the same trick work also with the calcium ions, but with the calcium ions we just cross-link with the calcium, and after this we can dissolve the calcium carbonate by adding the acid and start to be calcium alginate, but it start to be very soft gel particles. But with the silver we have a hard shell, which could give us a lot of interesting property, which I will talk later on. Here it is, we can see the more detailed image from the TM and ACM, how the shells look like. For example, here the black, it is a kind of TM images. We see that it's more of single particles inside, and it's really the glued together. Also, the red one, it's which it is a drug which are loaded before in calcium carbonate, which still, when we dissolve the calcium carbonate drug and or kind of model molecules like here the red, it's trisdextran, as I remember, still stay inside. Yeah. Okay, what we get as result? Since our idea was to control the shape and the size of the alginate capsules by the control of shape and the size of the calcium carbonate, we check it, how it is influenced. We take the calcium carbonate with the 3 different sizes, like the 0.8 micron, the 1 micron, and 3 micron, and check how it's influenced to the shape of the silver alginate hydrogel capsules. And really, as we expect, they completely repeat and slightly increase because, of course, we control the shell, which has kind of thickness. Sometimes the thickness is quite high, sometimes thickness it's not so high, but usually it is 100 to 200 nanometers could be, because the silver nanoparticles is quite big sometimes. And also we see that the loading of the nanoparticles in a red channel. They still load, they still have the fluorescence molecules inside. In our process, to absorption of the alginate, to cross-link, to dissolve the substance, not influence too much to the drug loading distribution. Yeah, we check the stability of our particles because in general, the calcium carbon by themselves, if we not dissolve them, have a chance to crystallize to the calcite and release our drug. For example, here to check it, we load them with enzyme, with alkaline phosphatase, which are very useful enzyme for bone reconstruction materials, because one of our ideas to apply such capsules as part of the bone implants. And we check the activity of enzyme, because one of them, it is how much drug stay inside, another one, how it's available by the kind of substrate molecules to activate them. And here it is, we check that how the calcium and the silver alginate layer provides the crystallization, and we check that they stabilize a lot, really, independently on the size of our particles. If we take the smaller and bigger one, like the half micron and kind of 3 microns, it's more of the same influence to the stability. And also the silver alginate provide kind of stability much more because the shell thickness of the shell is higher, and really we cover it with a kind of monolayer of the nanoparticles. When we check the activity of the alkaline phosphatase, of course, denser layer we have, less activity we have. In the case, if we need a slow release, or if we need the kind of protection of our enzyme, these methods work. If we need the quick and very intense activity of enzyme, these methods will be not so work in this step. Yeah, in the case depends on our goals, we can choose or cover them or not cover, and how much layers, for example, we can cover, how much density of alginate we'd like to have. This one, of course, depends on the concentration and amount of the molecules. But of course, for drug delivery, especially for theranostic concept, is very important to think how we will release our drug. Because sometimes, like the alkaline phosphatase, it just should be in a place and we don't need to release. It should be work longer. In the case of slow activity and protection, it will be very nice. And slow degradation of the alginate layer. But sometimes we need to release something very quick, especially when the capsules reach the correct place, like the cancer tumor. Really, one of the single and more efficient way how to release something in the body, how to influence something inside the body, stimulate release, it is ultrasound, because each hospital has a nice ultrasound, and you don't need additional treatment or kind of surgery to apply the ultrasound inside the body, inside the tumor. In the case, first of all, in this work, we will focus to the ultrasound release. And we think it's kind of good idea, because also we have connection of the metal and not metal and organic part with particles, and we think that the ultrasound will be isolate our metal particles and will destroy the shells. And it's happened like this. We check the, here it is in a plot, you can see the amount of the particles which are crushed, depends on the size. And of course, the bigger particles crushed much more quickly because they are less stable, less dense, because the layer of alginate and silver is quite the same. But small particles, they have more dense layer, and in the case they crush not so efficient. But really, all this destroyed, we use a kind of medical ultrasound, and also we check this ultrasound pass. In the case, it's very, very low intensity of the ultrasound. In the case, it's very efficient to use the particles to use a stimulative release by the ultrasound in medicine. Yeah. After this, we can think, okay, how we can provide them further medical application. Of course, when we start work with the silver alginate, a lot of people, I mean, from biology start ask us, okay, it's silver, it should be toxic for everywhere, it should be not uptake for the cells, because it's not like the calcium alginate, which are stable and friendly. Yeah, of course, they are slightly toxic. It's around 80% of the toxicity respect to the control, but it's still acceptable level. And of course, it's very toxic to the bacteria. Unfortunately, I'm not present this data here, but yeah, it's kill bacteria very nice. Of course, by the silver ions. But what is more important here is that such particles, such hard shells, still can penetrate inside the cell membranes. Here it is, you can see the images, how the different particles with different sizes penetrate inside the hello cells. And we see, of course, the smaller particles penetrate much more better rather than the big particles in the accumulation curve. And this one, 2 lines at 2 time points. Of course, it depends on time, they penetrate more. And it's understandable that the small particles penetrate better, but big particles, 3 microns, still penetrate, and we still have a kind of delivery inside the cells. After this, we go to the kind of small, more to the biological test, and it will be interesting how these particles work in more living kind of tissue in living organisms. And with our collaborators, we do the experiment with the C. elegans, it's small worms, which has big advantage for us in the laboratory because they are almost transparent. In the case, we can see the living tissue, living worms which are still alive under the microscope. We just slip them and can see how the particle distribute and it not. In the case, what we realize is that the worms like a lot to eat the alginate capsules, and they eat a lot and they penetrate inside their body, and we can see them inside. They are not toxic. The worm can survive for a long time. But our particles, also load here with the dye, and we can see that where they are. In the case after this, we're thinking, okay, could we release something inside the worm? And okay, we checked before that easily release something with ultrasound, but also we interested, okay, could we maybe release with a laser? Worm is transparent, and our particles full of the plasmon nanoparticles, silver nanoparticles in the shell, which will be very sensitive to the laser irradiation. And we apply laser irradiation and see that the drug start to be released around and was very successful in the fluorescence signal. In the case, we show that, okay, just 15 milliwatt, it's kind of it's not very strong laser. Possible, it's from the Raman microscopy laser in kind of not very high power. We can still destroy our particles, and our dye, the fluorescent dye, start to be released. Of course, inside the body and so on, it's very difficult to record really the kind of cloud of the dye near the particles. In the case, we just check by the profile and intensity how this dye spills around, because really there are a lot of compartments inside in tissues which do like to absorb this dye back, but the system is changed, it's definitely. But also we start thinking that since our particles has this plasmon nanoparticles and react to the laser well, maybe we can use the Sears effect to detect them. And we start thinking, okay, if we start scanning not loaded particles, which has 0 dye inside in our worm, we can recognize by the Raman signal where they are. It means that it's not Raman signal from the particles, it's Raman signal from the kind of compartment which adsorbed to the particles and amplified by the particle shell. In the case, it's a very interesting concept and very new, because our particles by themselves can be detectable by the Raman. It's kind of variable field detection and tracing, because we don't need to load them with any dye to understand how they distribute inside the kind of form tissue, because really they amplify all surroundings near the particles. In the case, we can just check where they have a strong Sears effect, and we can see the kind of light dots here. It is our particles in it. But Sears effect by themselves, it's also very interesting to use such particles as a sensors for detection of something. Because in a theranostic concept, it will be nice, for example, in a worm or where we can, or under the skin or the skin layer. For example, if we detect kind of bacteria, virus, or kind of necessary compound or cancer cells, after this we can apply them laser or ultrasound and release the drug. In the case, yeah, we have very nice density of the plasma nanoparticles on top, and for provide nice surface enhanced Raman spectroscopy, it will be nice if the particles has around few nanometers between each other, and we in our show we provide it, and we check the kind of spectra of the kind of target molecule. It was mercaptobenzolic molecule, and how the particles amplify. And we check that we can amplify the signal in 10 to 5, kind of in 10,000 and or 1 million times sometimes. But really, it's just to know that it's not pure signal amplification. It's named enhancement factor, which connect together a few factors. One of them is the signal amplification, how the intensity of our peak of the Raman, but together with how much power we need to use for this, for the same concentration. Because in a Raman we can use the power from kind of up to around 100 milliwatt, for example. But if we provide the same maximum intensity already in 0.1, it gives us around 1000 amplification in this signal. In the case, our particles provide very, very nice amplification up to 10 to 5, 10 to 6 amplitude, which means that we can detect with very small power kind of compounds inside, which means that we can apply very small power, which not destroys the particles, because for the particles we need 15 milliwatts to destroy. And start destroying the capsules only if we detect something. We can increase the power or apply the ultrasound. Okay, in conclusion, what I'd like to say is that it's possible to create very interesting template-based polymeric capsules based on the silver alginate or calcium alginate, which is possible to release substance by the ultrasound or by the laser, or use them as a sensor by themselves or label-free detection inside the bodies. Also, I'd like to say thank you to all my collaborators, which help in this work, which we do already many years in a row. Okay, and thank you very much for your attention.